Good morning, everyone. In this lecture, we are going to discuss about full wave controlled converter. In previous lectures, we discussed about your half wave controlled converter by using SCR. Okay, so we have already know that what is the difference between uncontrolled and controlled converters. So you can now able to understand what is controlled and uncontrolled converters. In controlled converters, we are using SCR, and we can easily control the output voltage, okay, by varying the triggering angle of SCR. But in uncontrolled converter, we were using diodes, so output voltage cannot be controlled by using diodes. Okay, that's why these those converter which use diodes, that is called your uncontrolled converter. So learning objective and outcome of this lecture is, after this lecture, I'm expecting from the students that they will be able to understand what is controlled and uncontrolled converters, and what is your half wave and full wave converter, and what is the difference between constructional and operational features of uncontrolled and controlled converters. They will be able to draw the waveforms and calculate their average and RMS values of the different variable associated with a single phase fully controlled and half wave converters. They will be able to explain the operating principle of a single phase fully controlled bridge converter, and they will be able to identify the mode of operation of the converter, which is continuous or discontinuous for a given load parameter and firing angle. And they will be able to analyze the converter operation in both continuous and discontinuous conduction mode, and thereby find out the average and RMS value of input or output voltage and currents. So first we come to the point, that is your half controlled converters. So what is your half controlled converter? I have already discussed in previous lectures that the diagram which is over here, that is your diagram B, that you can see in this diagram we are using two SCRs, T1, T3, and there is two diodes, D2 and D4. So the load is your RLE. Okay, so this is your half controlled converter. Okay, and this is also your half controlled converter, in which you are again using two SCR and two diodes, but uh, the sequence, or you can say the this diode is replaced by a thyristor, and this thyristor is replaced by a diode. So this is the minor difference between these two diagrams. So this is called your half controlled converters. In this you are using two SCR and two diodes. But in full controlled converters, you can see over here that we are using four SCRs, T1, T2, T3, and T4. In next slide, we will discuss how what is the working principle of these controlled converters. So you can see from this table that for a single phase half controlled converter, that it has two diodes and two SCR. One is your T1 and D2. So first we are taking that T1 and D2 is conducting. So when T1 and D2 is conducting, so the current will flow through this direction. Okay, the direction of current will be from T1 to load and then again D2. Okay, when T1 and D2 conducting, the voltage across these SCR and diode will be zero, and you will get the output voltage and output current over here. So you can see from this table that the voltage across VT1 is equal to 0, and the voltage across VD2 is equal to 0, but the voltage across VT3 is equal to minus V1, and the voltage across VD4 is equal to minus V1, and you are getting output voltage V0 is equal to V1. Okay, so this is for the conduction of T1 and D2. Now we come to the next point. This is your T1 and D4. So you can see over here that when T1 and D4, when T1 and D4 is conducting, like when simultaneously when these SCR and diode is conducting, then you can see over here that the direction of current will be this. Okay, okay. So you can see over here that the voltage across the SCR T1 is equal to 0, and the voltage across T3 will be minus 1, and the voltage across VD2 is equal to V1, and VD4 is equal to 0, and you are getting output voltage is 0. Why it is happening? Because you can see over here the circuit is not completed. Okay, so you will not get any output voltage. Now when T3 and D4 is conducting, T3 and D4, T3 and D4, or T3 and D4, the direction of current will be like this. Okay, the current direction will be like this, and you will get the output voltage, which is your minus V1. You can see that the direction of current is getting opposite. Okay, like this, T3 and T4. Okay. So the voltage direction will be opposite. Now we will discuss this diagram in detail in later. So we come to the first point, that is your single phase half wave controlled rectifier RL load with a freewheeling diode. So first we come to the diagram, this diagram. You can see that there is a supply voltage which is your AC voltage. This is your thyristor. One freewheeling diode is connected in this circuit diagram, and the freewheeling diode is connected in parallel with your RL load. So this is your resistance load, and the voltage across this SCR is equal to VT. The current which is supplying through this supply voltage, which is IS, the current which is flowing through the thyristor is IT, and the current which is flowing through the freewheeling diode, which is your IFT. And the current, output current which is flowing through this load is I naught, and the output voltage is your V naught. Okay. So first we will start from this positive half cycle. You can see in this diagram that Vs is your input voltage, V naught is your output voltage, this is your output current, this is your freewheeling diode, this is your input current, this is your freewheeling diode current, and this is your thyristor voltage. So first we will talk about this positive half cycle. Okay. So let's start from this positive half cycle. When you apply positive half cycle to this terminal, okay, so the terminal of this thyristor become positive and this terminal become negative. Okay, so this thyristor terminal become positive, this thyristor terminal is your negative terminal. Now what is happening? Until unless you apply the gate pulse over here, the thyristor will not turn on. Okay, so at the delay angle of alpha, we are applying gate pulse to the gate terminal of the SCR. Okay, so by after this angle alpha, when you apply gate pulse to this gate terminal of SCR gets turned on. Okay, SCR is gets turned on, and what is happening when it gets turned on? Then you are getting the output voltage from alpha to pi, because at pi the thyristor voltage, the input voltage is getting negative, so the this terminal of thyristor become negative, and thyristor comes into the reverse biasing from pi to 2 pi. Okay, so first we will discuss about for positive half cycle. So alpha to pi, you are getting output voltage and thyristor is conducting. That's why you are getting output current. Okay, this is your output current waveform. This is your input current. Okay, supply current you can say. Now, in this case, freewheeling diode is not conducting from alpha to pi. So the freewheeling diode current in this case will be 0. Fine. Now, in thyristor, for thyristor uh, 0 to alpha, thyristor was not conducting. So there is some voltage which is appearing across the SCR. Okay. But at alpha, you triggered the SCR and you are getting what you are getting? You are getting from alpha to pi, the thyristor voltage is equal to 0. So this is all about your positive half cycle. Now we come to the next negative half cycle. So you can see over here in the load, the inductor is connected and the property of inductor is that it always opposes the change of current. Okay. So in this cycle, in this positive cycle, the inductor was storing the energy. Okay. Now, when suddenly SCR will get turned off at this point, what is happening? The thyristor will not change the direction of current and the current will flow through this freewheeling diode because it getting the path to flow the current. And when it will behave like a source and negative voltage appears here, okay, so this diode becomes forward biasing and the current will start to flow from this circuit, freewheeling diode, resistance and this inductance. So you can see over here that in the negative half cycle, you are getting the output current. Okay. So in the negative half cycle, you are getting the output current. Again, at this point, again SCR sorry, at this point, the current is conducting through the freewheeling diode. So you can see over here that the current is conducting through the freewheeling diode until and unless your SCR gets turned on. At 2 pi plus alpha, again your SCR gets turned on because this is your positive cycle and it comes into the forward conduction mode. So current will start to flow through this SCR because this is your, because this is your uh, positive half cycle. So SCR will conduct and diode becomes in reverse bias. Fine. So by using the freewheeling diode, you can see that the uh, output current is not getting 0. Okay. So this mode is called your continuous current mode because your output voltage is not getting 0 anywhere in this waveform. You can see that the output current is not 0. So that's why this mode of conduction is called your continuous current mode. So we can see that the current that the circuit consists of a thyristor T and a voltage source Vs and a freewheeling diode across the load RL and an inductive load L and a resistive load R. During the positive half cycle of the input voltage, the thyristor T is forward biased, but it does not conduct until a gate signal is applied to it. So when a gate pulse is given to the thyristor T at omega T is equal to alpha, it gets turned on and begins to conduct. Now, when the thyristor is on, the input voltage is applied to the load, but due to the inductor present in the load, the current through the load builds up slowly. Now, during the negative half cycle, the thyristor T gets reverse bias and at instant at omega t is equal to pi, the load shifted to the freewheeling diode, from thyristor to the freewheeling diode. When the current is shifted from thyristor to freewheeling diode, the thyristor turns off. So the current through the inductor slowly decays to zero through the loop R, freewheeling diode, and L. So here the thyristor will not conduct in the negative half cycle and turns off at omega t is equal to pi. So the load receives voltage only during the positive half cycle, and the average value of output voltage can be varied by changing the angle of alpha. So the waveform shows in the diagram. This is your continuous conduction mode, and in the diagram I have already explained. This is your input voltage, output current, freewheeling diode, and your thyristor voltage. So I think now it is clear that how a thyristor will how a converter behave in with RL load with freewheeling diode. Now this is the equation. By using, you can do the mathematical analysis of these waveforms. So from the diagram that you can see, Vm sin omega t is equal to I naught R plus L di naught upon dt. So, as we know, the solution of this equation, that is equal to because this is your first order equation, so you can solve by mathematically, and you will get I naught is equal to Vm upon Z sine omega t minus 5 plus a e to the power minus 1 upon R by L into t. So at omega t is equal to alpha, I naught is equal to I naught. At t is equal to alpha upon omega, I naught is equal to I naught. So you can get the value of a, which is equal to I naught is minus Vm upon Z sine alpha minus phi into e to the power R alpha upon omega. Okay, so you can by solving this equation, you will get the expression for your output voltage, output current, which is Vm upon Z sine omega t minus phi plus uh, brackets I naught minus Vm upon Z sine alpha minus phi, bracket close, and the exponential of minus R upon L t minus alpha upon omega. So this is the equation for your output current. Now, in mode second, that was the mode first when freewheeling diode was not conducting. Now we come to the next part when freewheeling diode is conducting. So you know that the freewheeling diode is conducting from pi to 2 pi plus alpha, and the input voltage at this time is zero because the energy which is transferring to the diode is through the inductor. So the equation for this mode is equal to 0 is equal to I naught R plus L di naught upon dt. So its solution is, by solving this equation, you will get, which is the solution of this equation, I naught is equal to a e to the power minus R by L into t. So I naught is equal to I naught 1. So the equation for a is equal to I naught 1 e to the power pi R pi upon L omega. So finally you will get the equation for output current in for mode second, which is expressed by equation 6.12, and for mode second, the omega t will be greater than pi but less than 2 pi plus alpha, and average load voltage you can get from this equation, which is equal to Vm upon 2 pi into 1 plus cos alpha. Okay, now this is all about your single phase converter with freewheeling diode. Now we come to the next point, next converter, which is your single phase full wave controlled converter with R load. So we can see the diagram over here, that this is the diagram in which you can see that we are using four SCRs, T1, T2, T3, and T4, and the supply voltage is Vs. Okay, and the load which is connected to this converter is only resistive load. Okay, so what is happening in this diagram? First, why it is called full wave converter? First question is why it is called full wave converter. So when you will see in this in these waveform, or I'm going to explain that in this converter not only positive half cycle is converting into DC, as well as the negative half cycle of the input voltage is also converting into the DC voltage. Okay, I will explain you. So first we come to the these waveforms that you can see over here, that Vs is your input voltage. Okay, this is your positive half cycle and this is your negative half cycle. So 0 to pi the supply voltage is your positive, and from pi to 2 pi the supply voltage is your negative. Okay, so as you know, thyristor will conduct when you supply or apply any gate pulse to the SCR. Okay, so the gate pulse, you can see that this is IG1 and IG2, and this is your IG3 and IG4. So IG1 is the gate pulse for your SCR T1. IG2 is the gate pulse for your SCR T2, and IG3 is the gate pulse for your SCR T3, and IG4 is the gate pulse for your SCR T4. Okay, so at a time there will be two thyristor will be conduct. Okay, it may be your T1, T2 or T3, T4. So first we will discuss about this positive half cycle. Okay, so when the supply is your positive half cycle, so you can see that this terminal of your this point will be positive and this point will be negative. Okay, I mean this terminal will be positive terminal and this terminal will be your negative terminal. So you can see that when this terminal is your positive terminal, only T1 will be in the forward biasing. Okay, T1 will be in the forward biasing, and this T4 will be in reverse biasing. Fine. So T1 thyristor SCR T1 will be in forward biasing, and thyristor T4 will be in reverse biasing. Like this, this terminal is negative, so T2 will be in forward biasing and T3 will be in your reverse biasing. So you can see that when your supply is positive, only T1 and T2 will be in forward bias. So these SCR will conduct, and you can apply gate pulse to these SCR T1 and T2. So you can see here that we are applying gate pulse, which is your IG1 and IG2, to this positive half cycle. Okay, the delay angle is your alpha. Fine. When T1 and T2 conducts, the circuit completes through this load. Okay, so the circuit will be from supply voltage T1, resistance, and T2. This is your circuit which is completing through these components. Okay, so you will get the output voltage in this condition. You can see from alpha to pi you are getting your output voltage. Okay, now is it clear? Now we come to the next point. At pi you can see the output voltage is getting negative. Okay, sorry, the input voltage is getting negative. When input voltage getting negative, this terminal becomes negative and this terminal becomes positive. When this terminal become negative, T1 become reverse biasing and T2 becomes your reverse biasing. But when this terminal is your positive, T3 becomes your forward biasing and T4 becomes in your forward biasing because this terminal is negative. So after T1 and T2, T3 and T4 comes into the conduction mode for this negative half cycle. Fine. For this negative half cycle, T3 and T4 comes into the conduction mode. Now you can see from pi to 2 pi, we are applying gate pulse to the to T3 and T4 SCR. T3 and T4 SCR, and we are applying gate pulse over here. Now, in this case, you are getting this output voltage, which is pi plus alpha, and 2 pi. Which is pi plus alpha and 2 pi. Fine. After that, again, this cycle becomes positive, which is 2 pi to 3 pi and 3 pi to 4 pi. When this cycle becomes positive from 2 pi to 3 pi, again T1 and T2 will conduct, and we apply gate pulse to these thyristors, and you will get the output voltage. So you can see from this diagram or these waveforms that you are getting output DC voltage for both positive half cycle as well as negative half cycle. That's why this is called your full bridge converter. Okay. So the circuit consists of 4 SCRs, T1, T2, T3 and T4. The load voltage is R. At a time during positive half cycle, T1 and T2 will conduct. During negative half cycle, T3 and T4 will conduct. Okay. And the gate pulse which is applied at omega t is equal to alpha angle. So during the negative half cycle, T3 and T4 will remain forward biasing, and T1 and T2 gets reverse bias and turns on. Then when a gate pulse is given to the thyristor T3 and T4 at omega t is equal to pi plus alpha, it gets turned on and begins to conduct. When T3 and T4 is on, the input voltage is applied to the load Vs, T3 load, T4 and Vs. So here the load receives voltage during both the half cycles. So the average value of output voltage can be varied by varying the firing angle alpha. Now we come to the next next type of converter, which is your midpoint converter. Okay, so you can see in this diagram why this is called midpoint converter, because we are using a one transformer. This is the primary winding of transformer, and this is your negative winding of secondary winding of the transformer, and the secondary winding of transformer is divided in equal parts. That's why this is called midpoint converter. And here you are using only two SCRs, which is your T1 and T2, and the load which you are using, that is your R load, and the output voltage which you are getting across this midpoint converter is your V0, and the current which is flowing through this converter is your I0. Okay. So let's come to the waveform of a midpoint converter. Before going on this waveform, I think we must go through these two slides, right? So single phase full wave controlled rectifier midpoint converter. The circuit consists of two thyristors, which is your T1 and T2, which is connected to a center tap transformer and a voltage source Vs and a RL load. During the positive half cycle of the input voltage, the thyristor T1 will be in forward biasing, but it does not conduct unless you apply the gate pulse. When a gate pulse is given to the SCR at point alpha, at omega t is equal to alpha, it gets turned on and it begins to conduct. When the thyristor T1 is on, the input voltage is applied to the load, but due to the inductor present in the load, the current through the load builds up slowly through the path A T1 load and A. So during the negative half cycle, T2 is in forward biasing and the thyristor T1 gets reverse biased, but the current through the thyristor T1 is not zero due to the inductor and T1 does not turns off. So the current through the inductor begins to decay to zero and T1 conducts for a small duration in the negative half cycle. So when a gate pulse is given to the thyristor T2 at omega t is equal to pi plus alpha, then this conductor will start to conduct and it will get turned on. And when the thyristor T2 is turned on, the load current is shifted the path from T1 to T2. Okay, and the T1 gets turned off at pi plus alpha. When T2 is turned on, the current through the load builds up slowly and it will flow through the path of B, T2 load and B. So here both the thyristor will conduct for a few duration in the negative half cycle. So the load receives voltage during both the half cycles. So the average value of output voltage can be varied by varying the firing angle alpha. So now the point is that during this positive half cycle, you can see that it is conducting from 0 to pi. Okay. So when we apply positive voltage in this circuit, then this terminal become positive and this terminal become negative. Okay. For this terminal become positive and this terminal become negative for positive half cycle. So for positive half cycle, T1 will be in the forward biasing. So when T1 is in forward biasing and you are not applying any gate pulse over here, T1 will not conduct. But when you apply gate pulse at T1, thyristor will start to conduct. So you can see in the diagram at point alpha, you are triggering this SCR T1 and it will start to conduct. So it will conduct from alpha to pi. But you are getting the output voltage when T1 is at pi, after pi. Why it is happening? You can see in the diagram the load is your inductive. Okay, when the load is your inductive, due to this inductor, the thyristor will not turned off at this point. Okay, so it will conduct in the negative direction, and you can see that you are getting the output current from pi plus L. But at this point, you are triggering another SCR, which is your T2. Okay, so when T2 gets turned on, the you are getting the current. Okay, you are getting the output current. You are getting the output voltage from pi plus alpha to 2 pi. Okay, so you can see here the current is also in continuous conduction mode when you are using RL load in midpoint type converter. Okay, now this is very important equations for this midpoint type converter, that suppose this is your point A and this is your end point, this is your B. The voltage across these two points is called your BAN. The voltage across these points is called VBN. So from this equation, you can see that VAN is equal to Vm sine omega t and VBN is equal to minus VNB. Okay. So when from the diagram, when the voltage across this terminal is positive, then at the same time the voltage across this terminal will be negative. So when VAN is equal to Vm sine omega t, the voltage across VBN will be negative. It will be minus Vm sine omega. So the total voltage across these two terminal becomes the difference of these two terminal, VA minus VB. it becomes 2 Vm sine omega t, which is double of input voltage. So when omega t is equal to alpha, T1 is triggered, SCR T2 is subjected to a reverse voltage VAB, which is equal to 2 Vm sine alpha, as stated before. So current is transformed from T2 to T1, and as a result T2 is turned off. The magnitude of reverse voltage across T2 can also be obtained by applying KVL to the loop and the equivalent circuit at the instant T1 is triggered. I have already explained. Okay. So the total voltage is equal to when you apply KVL across this loop. Okay. When you apply KVL across this loop, you will get this equation, which is equal to VT2 minus VBN plus VT1 is equal to 0. So voltage across thyristor is equal to VBN minus VAN plus VT1. So with T1 conducting, VT1 is equal to 0. Therefore, the voltage across T2 at the instant omega t is equal to alpha can be seen by VT2 is equal to minus Vm sine alpha minus Vm sine alpha, which is equal to minus 2 Vm sine alpha. So you can see that when thyristor T1 is conducting, the double voltage, which is negative, is appearing across this SCR, which is equal to minus 2 Vm sine alpha. So this shows that the SCR T2, when it is reverse bias, the voltage 2 Vm sine alpha appears across it, and it is therefore turned off at omega is equal to alpha. So thyristor T1 conducts from alpha to pi plus alpha. After omega t is equal to pi, T1 is in reverse bias, but it will continue conduction due to forward bias. SCR T2 is not triggered, and inductor is also present in this load. So at omega t is equal to pi plus alpha, T2 is triggered and T1 becomes reverse biasing, and the voltage which is appearing across the T1 is equal to 2 Vm sine alpha. So this is all about your midpoint type converter. Okay. Now we can compare these converters to each other. That the SCR has in midpoint converter, actually SCR has are subjected to a peak inverse voltage, which is 2 EM or 2 VM. You can say 2 VM or 2 EM in midpoint converter, and is fully controlled bridge converter. If you talk about fully bridge controlled converter, the voltage will appear across fully bridge controlled converter will be VM. Okay. Next, the in midpoint configuration, each secondary should be able to supply the load power. As such, the transformer rating in midpoint converter is double the load rating. So it is not in the case of single phase bridge converter. The single phase bridge converter we will discuss in the next lecture. So now I want to summarize this lecture that yes. So I want to summarize this lecture that in previous lecture we discussed about half wave controlled converter and uncontrolled converter. In uncontrolled converter we were using a diode. If you want full wave uncontrolled converter, then you have to use two diode. If you want to uh, if you want to use controlled converter, then you have to use some SCRs. If it is half wave, then you have to use one SCR. If it is full wave, then you have to use two or four SCR, which will depend upon the uh, configuration of your converter. Okay. So in full converter, the positive waveform and the negative waveform both were converting into the DC, DC current. Okay. So basically, converter is a converter or rectifier is a AC to DC converter. Okay. In controlled converter, you are using SCRs, and if it is full half converter, then you are using two SCRs or two diodes. If you are using if you want to convert your negative cycle also, then it will use two 4 SCR instead of two SCRs. Okay, so you can see in the diagram that in this lecture we have discussed about half controlled converters. Okay, these are your half controlled converters. Now, freewheeling single phase half wave controlled rectifier with freewheeling diode, in which you were using only, you were converting only half positive cycle into the DC. Okay, positive cycle into the DC, and you were getting output voltage only for this positive half cycle. That's why this is called your single phase half wave controlled rectifier. Next one was your single phase full wave control rectifier with R load. So this was your full wave controlled rectifier with R load. Okay, in which you were getting the output voltage in for both positive and negative half cycle. And this is your midpoint converter. In this also you are getting the output voltage for positive and negative cycle. So now you can there are some applications for full bridge converter. So single phase fully controlled bridge converter are widely used in many industrial applications. They can supply unidirectional current with both positive and negative voltage polarity. So they can operate either as a controlled rectifier or as an inverter. We will discuss the inverting mode of these converter in the next lecture. So, however, many of the industrial applications do not utilize the inverter mode application operation capability of the fully controlled converter. In such situations, a fully controlled converter with four thyristors and their associates control and gate drive circuit is definitely a more complex and expensive propositions. So single phase fully controlled converters have other disadvantages as well as relatively poor output voltage, form factor and input power factor. So this is all about your today lecture. Now there are some few questions which is based on today's lecture. So first question is your, the below shown single phase controlled rectifier configuration is a, you can see that is your midpoint type converter. So this is your single pulse midpoint connection or two pulse midpoint connection. So you are getting output voltage for positive and negative cycle as well as, so this is your two pulse midpoint connection. Second, in the below shown circuit, considering the load to be purely resistive, the thyristor T2 would conduct from, so this is your midpoint converter, and the thyristor T1 which was conducting from alpha to pi. Okay. For a single pulse midpoint type rectifier with RL load and firing angle alpha is greater than 0, the value of the inductance L is such that the load current is continuous. So choose the correct statement. The load current can never be positive. The load current can never be negative. The load current can never be zero. The load current is a constant DC. So we have already discussed in this converter, because the inductor is connecting over here. So the load current can never be zero. Voltage might be can negative in this uh, midpoint type converter, but your current will never be zero. So that was your continuous conduction mode. Okay. Now come to the next question. So for the circuit below, the transformer ratio is 1:1. Okay. Vs is equal to Vm sine omega t. When T1 is forward biased and is triggered at alpha, then T2 is subjected to a forward voltage of Vm sine alpha. When T1 is forward biasing and is triggered at alpha, so you can see when T1 is triggered at alpha, this becomes in forward biasing and this will become in the negative biasing, reverse biasing. So T2 will be in reverse bias, but the voltage which will appear across this, it will be 2 Vm sine alpha. So the correct answer is it will subjected to a reverse voltage of Vm sine alpha. Okay. Now come to the next question. The circuit turn off of M2 type connection is, okay, the circuit turn off M2 type of connection is midpoint. Actually, the circuit turn off time always greater than the thyristor turn off time. So it will be pi minus alpha upon omega. So this is the correct answer for that. Now, next question is, find the expression for the average value of the output voltage for the below given circuit. Consider the load current to be continuous. Firing angle is alpha. Transformer ratio is 1:1 and Vs is equal to Vm sine omega t. So you have seen from the equation that output voltage for the below circuit, consider the load current to be continuous and firing angle is alpha. So average value of output voltage we have already discussed. You can see that for midpoint converter, okay, it is not given here, but I'm telling you that when you solve this equation for this midpoint converter, you will get the 2 Vm upon pi cos alpha for this midpoint type of converter. Now, a fully controlled converter uses diodes only, thyristor only. It will uses thyristors only. Okay, there will be no diode if it is fully controlled converter. Now, next question. A single phase full converter using R load is a quadrant converter, and that using an RL load without freewheeling diode is a quadrant. So this is your one quadrant and this is your two quadrant. Because in this case, in the RL load, the voltage is also going into the negative direction, but the current was also positive. Okay, so it will conduct in a one quadrant and it will conduct in a two quadrant. So the right answer for this question is your C. Now, a single phase full controlled bridge converter B2 uses full controlled bridge converter uses that use 4 SCRs. Okay, bridge type converter we have already discussed. Now the last question is, in a B2 type full controlled bridge converter, one SCR conducts at a time, two SCR conducts at a time, three SCR conducts at a time, four SCR conduct at a time. Two SCRs conduct at a time. Okay. So this is all about your today's lecture, which is your converters, half wave and full wave converters. Thank you. These are the references book, which is your B.R. Gupta of Power Electronics and NPTEL lectures, which you can find easily on internet. So you can go through these two references and you can uh, get the lecture topics. Okay. So thank you.